Okay, so I'm going to finish up by talking about a couple of other examples of higher order functions. So if you remember back to when we wrote merge sort, right? So merge sort was the idea was our divide and combine sorting algorithm, divide the list into two piles, merge sort recursively, merge back together. How do we divide the list into two piles? That was just dealing cards into one pile or the other repeatedly. How do we merge back together? We look at the two lists. If they're one's empty, then the result's the other. Otherwise, you look at the two head elements to figure out which one goes first, and then recursively merge whatever's left over. So when we're talking about polymorphism, the Tuesday before the midterm, before spring break, we said, oh, wouldn't it be nice if we could make this polymorphic and make it so that merge sort works for lists of anything. And for split, that's fine because we don't do anything with the elements of the list when we're splitting it. It's just structural. It's just one element goes here, one element goes there, one element goes here, one element goes there. But for merge, we got stuck because if we try to say this works for lists with any elements, then what we're forgetting here is that we need to be able to test whether x is less than y. But now that we have higher order functions, we can do that because what we do is we make merge polymorphic, but also pass in a less than function. As an input. And so basically what we're saying is you have to tell merge what less than means. And then we just keep that same thing going there through all of the recursive calls. And so what this means is that then, well, if we're passing a less than function into merge, then we also need to put one into merge sort, and merge sort will have to set it down to its recursive calls, and merge will also have to pass it in. Okay, so if I plumb that through, yep, we're good. Okay, so now I can say, for example, I would like to merge sort with the function that sends xy to x is less than y, and I get things sorted into increasing order. But if, for example, I pass in the greater than function as my comparison function there, so I say that x is less than y, which one should go first, really means greater than, then it sorts it into the other order. And if I had a list of strings, well, then I can still pass in greater than, but in that case, it's really the greater than for strings rather than for lists. So I can make merge sort polymorphic, but I have to at the same time make it a higher order function, that is, make it take a function as input so that I can pass in the less than. In a slightly different design that we could have used here is use, you don't actually have to define this, it's built in, but we could define it to use a type order for the less than function, in which case it's typical to call this a comparison function. So let's replace less than with compare. And so then when we do the comparison function, the options are mm, so the options for the order type are less, equal, or greater, rather than just being true or false for a less than. And the reason that we might want the order type is that it turns out to work a lot better for tree algorithms, because for tree algorithms, often you want to know, like, is the thing I'm looking for at the root, or do I go left, or do I go right, which is exactly the equal or less or greater cases, respectively. And so then we can do the same kind of thing, except there's a built-in called int.compare, which is the comparison on numbers. Now int.compare actually works on the like built-in order type, which is isomorphic to that, but not exactly the same as it. So let me comment out my let me comment out my copy of it there, and then if we load there, then we can just pass in int.compare there. Okay, so in the homework, you'll be using a sorting library function that is like this merge sort, in the sense that it takes a comparison function which returns less, equal, or greater, but there's an int.compare there that you can use to do comparisons. Okay, point being just that, like, now we can say we can merge sort lists of any element you want, as long as you can figure out how to compare two of them and order them, because merge sort is a comparison based sort. So that's another example of a higher order function of a template of a pattern of computation, where now we can make merge sort more general and make it work for lists of anything that you can compare. And so one final example I want to talk about of higher order functions is, if you go back to the handout code for homework 6, the one that you just finished, then you wrote the show function that turned a model into a string, and the respond function that took a model and a line of text and updated the model, and took a model state and um, updated the model state. But then, like, there was a run, and that did some magic that like made interactions happen. And we won't talk yet about the functions that are making the interactions happen. But the thing I want to remark on is just that the overall driver here, the thing that read printed out the state of the model using your show function, and then read a line of input and used your respond function to uh, update the model based on the input. This string substring nonsense is just getting rid of the new line character that would otherwise be at the end of the string. Okay, so what is this like thing? This is the outer loop that like read in a line, printed stuff out, read a line of text, printed stuff out, read a line of text, printed stuff out, read a line of text over and over and over again. What that overall loop is a higher order function, because what it's doing is it's saying that you tell Go how to show a model and how to respond to a string input and give it an initial model to start with. And then this overall loop is just like a little bit of code that works with those. So the way in which I could write a single piece of code that was the driver that did the loop of printing and reading lines of input, both for the password example that we did in lecture and for the, um, what was it, for like the grocery store example that you did in the homework, was by using a higher order function that took in the show function and the respond function and the initial model, which is just a value, and then did the loop. So that's another example where I could write some code that worked for, was more general, like you didn't have to copy and paste this for your specific model definition. We could use the same function for the one we did in class and for the one that you did in the homework, because this outer loop doesn't really care what the model type is specifically, it just cares that the model type supports a toString function for showing it on the screen and a responding to text function for updating it, and has an initial model, and then you're off to the races. So this is another example where we can reduce code duplication. Instead of writing the same thing over and over and over again for different model types and different show and respond functions, we can write it once, give it as inputs functions that do the showing and responding, and then you just write those as the mm, for writing your particular application, you just write those, and then you give them to the Go function and let it uh, do the driver. Okay, so now we've seen a bunch of examples of higher order functions, as that is functions as arguments to other functions. We've written some more higher order functions today, like filter and reduce, and we've solved problems by chaining together a pipeline of functions, like the adding one to numbers less than 7 and the word count one. And we've also seen another higher order function sorting parametrized by an order type. So what you're going to look at in the homework is, again, this process of going from examples that have a lot in common to a single higher order function. So we're going to look at some tree code, so map and reduce for trees rather than for lists. So it should be the same idea, except as map is turn each element into a new element that's processed by a function, and reduce is summarize all of the values into data structure as one value, except you're going to look at it for trees instead of for lists. And then you're going to do a bunch of problems that ask you to write some code by doing maps and doing reduces and then writing some other functions and then putting those all together. And somewhere in there, some sorting for trees will come up. And the sorting function that you're given takes a comparison function that takes two elements and orders them using order, like we talked about here. Okay, so that's the homework. So we've more or less gone over the lab solutions in these videos, but you could have a look at the lab solutions. There's one other example of a stock market problem, which is an example of a slightly bigger function that you can write as a pipeline of maps and reduces and stuff like that. And so you could look at that in the notes. When you're looking at the notes, we're not doing the currying bit that it talks about there until next week, but it does do the stock market problem in the uncurried style at the very end as well. So you can read the problem description and then skip to the code that is uncurried at the end there to be on track with what we've covered so far. I'll do a little bit on currying in the video for next week's homework instead, because we don't need to do it yet. Okay, so you should be ready to work on homework 7 now. It's due next week at the usual time, and the lab solutions are up if you want to look at the lab solutions in code form, and hopefully talking through them a little bit here will help with the homework. Okay, talk to you all later. Hope you have a good week.